Good afternoon, everybody. Well, after all of the very interesting discussions today, I feel like a bit of a kindergarten child here because I think I'm going to be dumbing down a few things. So bear with me. I'm really going to try and sow a new seed today. I hope this moment will change the world. You can tell me afterwards whether I've achieved it or not. So what I'm going to talk about is the generation and transmission problem in general. For the world that's completely changed from the world I grew up in when I started in the electricity industry in 1977. Yes, I think I'm the old dog learning new tricks at the moment. That's how I feel anyway. So I'm at Monash University researching issues around the electricity industry. My focus at the moment is on generation transmission planning, and I've also been looking at modelling isolated solar battery systems, which I will talk about tomorrow. They're very kindly given me 2 shots at this conference, which is amazing. So let's have a look. So the generation and transmission problem for electricity faces an extraordinary list of uncertainties. Not only have we got questions about economic growth, we've got changes in technology costs, we've got technology transformation where whole new technologies are being developed and upgraded. We've got potential breakthroughs in distributed storage. There's about 20 different solar technologies which are being researched in universities, and any one of them could suddenly break through to lower cost and higher efficiency and displace existing technologies. We've got, in Australia, we've decided to flog all our gas to the rest of the world, so we've got much higher gas costs into our power generation than anyone really anticipated 5 years ago. And we've got complete confusion about emission abatement objectives at the political level. And of course, everybody says there's no government policy. Well, there is a government policy. It's to do as little as possible in emission abatement and pretend it'll all go away. So we're in a situation where running a few scenarios of this extraordinary range of futures is largely limited to, well, something in the middle which looks like will happen with minimal change, something that could be a lot higher for production and something that could be much lower than production. But the problem I see is that doing 3 or 4 long-term, internally consistent scenarios may not give us the information that we really need to present our results to our stakeholders, to the politicians and to the investors. And the problem is that transmission assets are really long-lived. They're going to be around for 50 or 60 years. And we're struggling to even see what the world will look like in 10 years. So how can I have confidence in a 60-year investment when beyond 10 years is almost a total fog? And there are questions like, because we've got to redesign some of our networks, we need to think about, well, where are we going to need new power line easements? I mean, in Victoria, we haven't bought easements since the 1950s. So how are we going to even value easements in this environment? And I would have thought we should be looking to work out what easements we're going to need, and we should be lining them up now, well in advance of their need. But that's really difficult in the context of this extraordinary range of uncertainty. So when we think about the current planning problem, and I'm talking in the context of Victoria, but it's the same in a lot of other places too. We're moving from fossil fuel generation in one location to renewables in another location. We can't even expect to fully use the current transmission capacity that we have. And we saw in the material that Stephen showed us earlier about how all that wind is right at the fringe of the 2 interconnections, where there's no grid capacity. What a rotten inconvenience that is. And we've got the same situation in Victoria. We've got our Western grid was designed to supply a few remote villages. And now people want to put 5,000 megawatts of generation on it. Oh, whoa, hold back. That's not going to work. So even for a low growth outlook, we still need to think about transmission developments. So the traditional approach is to try and do composite generation and transmission planning, and we've got the excellent capabilities of our optimisation tools to be able to sort that out. And so the situation is that we've got a kind of a market division. We do our generation competitively, where people make independent decisions based on market forecasts. And because networks are a natural monopoly, we have regulators who oversee the development of the network and want to see an economic justification for transmission. And so we have a bit of a chicken and egg problem when we're looking at moving generation to new regions. Can we expect competitive generators to build capacity where there's no network and just rely on the confidence in the regulator to bring the network to them? That might not work. Are we going to invest a couple of $1 billion in a new network in Victoria and hope that the generators come along and just follow the grid? Well, this of course has prompted the integrated system plan that AEMO has tried to develop after the Finkel review to try and give us some understanding about how the chickens and the eggs can work together to produce food. So we have scenarios of key uncertainties that we've used for that, and we've developed some robust combinations of new generation and transmission. Job done. Or is it? Well, I would submit that there's one question to be asked that no one knows how to answer yet, and that is, what would invalidate the longer-term components of the plan? For example, the plan's made up of 3 groups of projects, 1, 2 and 3. The Group 1 projects are no-brainers. They should have been worked on a few years ago. They provide immediate economic benefits for almost any conceivable scenario because they deal with current problems. So that's a few upgrades on New South Wales and Queensland. I don't think I've got a cursor I can wave around. Can you see that arrow? No. Flew off the screen, did it? No, it's pointing here, but you can't see it there. So we've got upgrades between New South Wales and Queensland, and we've got upgrades between Victoria and New South Wales, and we've got a 500 kV link out into Western Victoria to pick up new renewable energy. That's easy. Then we've got another group of projects that are basically an east-west highway to take account or take the value from the diversity of solar resources between South Australia and New South Wales and Victoria. Some further upgrades up between New South Wales and Queensland. And then we've got a whole lot of infills and augmentations which would be needed sometime in the mid-30s depending on how rapidly the market evolves. Now, we can commit to those now, that's not a problem. These ones we've got a couple of years to think about, and these ones will take some more work to refine and plan. So, the question is, well, what would invalidate the plan? We don't really know. So I'm going to skip through these a bit. I've indicated the Group 1s we've talked about. The Group 2 projects mostly have long lead times, so they're going to take a while to develop. They also support the upgrade of the Snowy Mountain scheme called Snowy 2.0. I think most of you will have heard of that. And there's a medium risk in those projects. The river link, so-called between east and west, has probably got a pretty strong case because of the inherent diversity of solar power across the interconnection. But still, it's a lot of money, and again, are we sure it's going to be needed when it's built? And the Group 3 projects are really needed to open up the network to the new zones and to support inter-regional trading. Fortunately, their need is well outside the lead time, so we've got time to think about those. But might the priorities change, and are the value drivers clear? So I'm proposing an alternative formulation of the analysis. So what I'm saying is that we've got demand uncertainty and all these technology uncertainties. So let's reduce the problem of the planning decision to a single year analysis. So we focus on single years for the critical conditions. So for example, in Victoria, our solar power in winter is only about a third of what it is in summer. So when we've got a high solar system, winter will be the critical period. We've got low wind periods. Generally, our wind generation's a bit lower in autumn. And then we have our high temperature summer for peak shortage of power for high demands. And we've got some low temperature limits in winter. So they kind of conceptually represent the critical times of the year. So what I propose we do is identify the key uncertainties such as demand growth, which represents our time horizon, our growth in distributed resources, which represents our uncertainty about what customers do for themselves and to the extent to which they become prosumers, as we call them. The costs of large-scale renewables. As you probably know, many of you know, the wind technology is still developing. The solar technology with photovoltaic is still subject to some possible disruption, and solar thermal is yet to really emerge as a competitive technology, but could. We've got nuclear power as in the mix if we're going to consider that as an option. In Australia, that's kind of not a serious proposition because it would probably take 15 years just to get the regulatory environment past the social and political opposition which you would invariably face. And in reality, we probably don't need to go nuclear anyway. We've got the cost of storage. We've got decisions people might make about electric vehicles. We've got uncertainties in fuel cost, particularly with gas, because we've got a looming gas shortage in Australia now with all these exports driving the LNG plants. Some coal uncertainty. Coal's an internationally traded commodity in Australia, so as our low-cost, lower quality resources are used up, increasingly our coal cost will get linked to its international value. And then we've got our emission abatement targets and policies sitting over all of that, which could push us one way or the other. So what I'm suggesting we do is we set up a set of studies where those are the uncertain variables. We optimise for single years, we parameterise those uncertainties, and we generate a number of either randomly or intentionally selected combinations of those uncertainties. And then if we are running in Plexos framework, we'd run an LT plan not for 5 years or 7 years, but just for 1 year. And if we were confident enough, we may even be able to cut out half the year as being not a driver of an investment decision, particularly as we get less and less fossil fuel and more renewables. Eventually we'll get to a situation where the marginal cost is always zero and it's just a capacity question, not really about displacing fuel costs. So we'd run unit commitment, our generation transmission option, and we get a single optimal design for each year for each random combination of these analyses. And so what we would then do is use pattern recognition techniques to understand the relationship between the results and the inputs. Now I'm going to give you a very simple example because I'm not a highly skilled person in this space. I'm just a humble electrical engineer pretending to be an economist. So I just kind of stumble along as best I can. Fortunately, I've got some really bright PhD students in our team at Monash who hopefully will take my ideas and run with them one day, probably long after I'm gone, hopefully. So, simple system, 6 buses, 3 generation nodes, 3 load nodes. So I set up this model with the help of my colleague, Eddie Lamb at Monash. And we did 20 simulations, very detailed unit commitment and investment analysis. I think his models took about 6 or 8 hours to run for this 6-bus system. So it was very detailed analysis. And we've got 3 coal generators, which we are not changing. They stay as put. We've got 2 CCGT options at bus 2 and 3. We've got 5 line options, which are the dotted lines in the diagram, just single upgrades to the lines. We had 2 wind farms at buses 4 and 5 associated with the load areas, and the energy storage we actually only did at 4 and 5, so we didn't model storage on bus 3 just to simplify the problem. So what we did that full analysis with all of those options, and I chose 5 random variables: the demand, the CCGT capex, the wind capex, the storage capex, and the gas cost as being the main uncertainties in that market. And then I ran 20 simulations and then I looked at the results. I used 2 methods to analyse them. I used linear regression, which is the simplest thing you can possibly do and easy to do. And I also taught myself about regression trees, something I hadn't heard of 12 months ago. And so I taught myself about regression trees and I started to use those. How many people know what regression trees are? 2 people know. Okay, I better explain, hadn't I? Okay, so first of all, this is really one of the really simple examples, and this is what the world would have looked like back in the 1980s when I was working on this stuff. This is the line between buses 2 and 3, and so all I did was the line is either 1 or 0, it's either in or it's out in each of those 20 simulations, and I just linear regression using 1 or 0 as the dependent variable. And in fact, when I did that linear regression, which is the tables up the top, I found that demand was the only significant variable in determining that. I got an R squared which wasn't too bad, 0.87 sort of all right, and it correctly identified every case. So it was perfectly good for the 20 cases. And these are the 20 random combinations looking at two of the variables, the demand, which was the determining one, and fuel cost, which I think was the next most significant, if I remember. Not quite. No, wind cost was more significant, but as it turned out, there were no wind farms turned up in the solution in this case, so that was a bit of a disappointment. So fuel cost was the next most significant, and so you can see that quite clearly above this demand level the line was in and below it it was out. So really simple. You just have to explain to people when the demand gets above that we build the line. It doesn't matter about any of the other variables. Don't care. Not interested. Okay, so that's really, really easy. Really, really easy. Very, very reassuring, I thought. Yeah, simple stuff might actually work. So next one was line 2 to 4. This was a bit more interesting. The R squared was quite ordinary. So linear regression was of no help at all. Now what the regression tree method does is it tries to split the solutions into two cases and it finds the divisional point where they are most different. That's all it really does. So in this case, what the regression tree did was started with demand and looked at all the demand values to see where it would most split the cases. And it found 3 demand levels at which it would split the cases. And that meant that below this level there was no line, in this range there was 1, in this range there was no line, and above 1.6 there was 1 line. The line was built in those lines. So you can see that that's quite nonlinear, so it's not surprising that the linear regression was of no help to us. But it also showed from that fuel cost was almost a determining value, but not quite. So that's why I chose fuel cost for the diagram. But these fit neatly into bands, and again, all the other uncertain variables had no effect on the answer. So that's sort of really interesting. What it means is that if the load gets to this level and you build that line and it stops growing, you're probably okay. If the growth finishes up in this region and keeps at that level indefinitely, then there might be questions about whether the line was still viable. If you've got a high growth scenario, then you're more than likely to eventually move into this space where that line is part of the optimal solution. So that's kind of useful as well. But again, that's really simple and easy to understand. The CCGT at bus 2 was also really, really easy. The R squared was good for linear regression. 85% of the solutions were correct. And they were basically entirely determined by demand, and the other variables had no real effect. So this CCGT decision, again, you just have to track demand, and that'll appear in the optimal solution above that level. That's nice. This one's a bit more complicated, and in this case, the regression tree split the area up into some more boxes. So in this case, for the CCGT at bus 6, the R squared was poor for the linear regression, so obviously the relationship's more complicated. This diagram's a bit hard to read, but you can see that for these combinations here, two units were built. Over in this space, 1 unit was built. Down here, none were built. So this separated out the with CCGT from no CCGT, so that kind of works neatly. So there's 2 in this band here, and there's either 1 or 0 in this band, depending on the CCGT capex. So this particular band here divided the space into 0 on that side and just a 1 on that side. That's not a terribly robust split, and probably what you'd want to do is run more samples to be sure that that's statistically significant. But at least it helps you to understand what are the key drivers for this plant, and certainly two units are desirable in this band, and so this is the critical level at which you'd consider building that plant. The battery was also a bit more complicated. Battery had storage cost and fuel cost as being the main factors influencing the value of a battery configuration. Demand wasn't a significant driver, didn't have a very significant component of the R squared. The linear regression wasn't much help in this case. Only 55% of the cases are correctly represented by linear regression. And in this case, we have one battery for high demand, two here. We have a band here where the battery's not part of the optimal solution. And interestingly, storage cost, for low storage cost, there's more batteries, which kind of makes sense, doesn't it? If storage is cheap, then you're going to have more. Even if storage is more expensive, you still can have batteries, but that would correspond to the other uncertainties being favourable for the battery solution. And there's a band on storage cost in the middle where batteries are not economic. By the way, one kind of represents storage cost as they are now. So the ranges were basically started from 1 and then deviate from there. And then for the low storage cost, low fuel cost also helped to drive the battery as well. And you think that might make sense if you've got low fuel cost, maybe you're using the gas turbine plant to charge the battery, and the battery is more valuable in that scenario as well. So that gives you some insight about that. I'm going to skip over that one because we're running out of time, and I want to go to this one. This is the other battery at bus 5. This one got a bit more interesting. The key value drivers for this battery were not like at the other bus, interestingly enough. So the key drivers there were demand and storage cost, and that may well be because at that bus there's a higher demand and the battery serves the purposes of getting to that node, perhaps because there's a limit on the transmission capacity. In this case, there's a kind of a slope characteristic. Now, these lines were developed by taking the linear equation, averaging the non-participating variables and putting them on the constant term, and just using the coefficients of storage cost and demand that came out of the linear regression. I think if I go back, the linear regression for this battery 5 was 0.74. So that wasn't too bad, 75% correct for the linear regression. So this gives you pretty much 0 here, transitioning from 0 to 2 in here, and then clearly 2 out there. If you look at that and look at those slopes a bit more carefully, I found if you draw lines, the dotted lines, rather than using the linear regression coefficients, then you can more precisely separate out the regions. So this is the 0 region here, that's the 1 in there, and that's the 2 above the dotted line. So it means that, by that means you can say, well, this is the investment plan. I'm going to do a battery at 5, but if the storage cost gets out of hand and the demand doesn't grow, then I'll scratch that project from my investment plan because it's clearly not going to work. So, in summary, what I found from this very, very simple analysis is that demand is almost always a key value driver. And that's good because that's the world we knew, wasn't it, 20 years ago? Demand was always the value driver. So it's reassuring that these methods confirm that. The linear regression identifies the key drivers in almost all cases based on the more significant variables, but it doesn't always reliably represent the number of options chosen if you just use it in that very simple approach, and only works at about 55 to 85% reliability for the sampled cases. The regression tree method, which divides up that space of uncertainties into boxes with similar numbers of options, or whether the option's in or out, that also works effectively to identify the key drivers and provides a more accurate separation of the relevant combinations of uncertain variables to provide a useful prediction. Usually both methods agreed on the key drivers, which was good, and we found in a couple of cases that linear combinations of two variables are sometimes more useful to indicate that where you can get a clear distinction between the number of projects that you would develop. And so the multivariable regression tree splits are more useful. Some other observations. Wind power projects were not included in the solutions. So I think that may have just reflected the size of the system, that it was probably wasn't big enough to cope with the variability of wind. And also it was useful that batteries came in at high demand and low storage cost which may have deferred line upgrades. So the interaction between storage and transmission was reflected in the results. So what I'm thinking is if we construct our studies in this form, and then if we can identify the patterns between projects being viable and the underlying uncertainties, then we can quickly construct long-term scenarios. We can work out the timing of projects. We can work out the risk of stranding. We can then rapidly construct long-term scenarios for the more detailed next level analysis when we get down to doing, the time sequential work and the more detailed studies. And I think we not only will be able to know what would not work, what would make a project invalid, but we can probably also more easily quantify the risk of an investment becoming stranded. So I'll stop there. Thank you very much. I hope you found that of interest.